Hello, friends, and welcome to Global Hack Week Machine Learning, What's That House Worth? Part 3. Hello, Polar Void. It's good to see you. Welcome, welcome. I am super excited for today because we get into it. I will say, here's the way that I will frame this is in part 1, we were programmers. In part 2, we were data scientists. And then now, finally, in part 3, we become machine learning engineers, machine learning practitioners, what have you. And so that is super exciting for me. We will check back in with our Kaggle competition, and then we will figure out how to improve our predictions. If you remember, I believe last time we set up sort of a very, very simple model where we just said, like, well, what's the average house price? And we just ran with that. But today we're going to get a little bit smarter about it because, I mean, in the very vague sense, you could say that taking an average is kind of like machine learning. But I think most people would judge you for that. Although we will define machine learning today. I feel like every Global Hack Week, I have to define machine learning. Otherwise, what am I doing, you know? Beverage check. What are you drinking? I'm drinking some very icy water. Ooh, actually, okay. So I am interested in hearing what everybody's drinking. I am also interested in whether or not you put ice in water and what country you're from. I imagine that we're pretty skewed to States and India, probably. Well, this time of day, maybe not India, but yeah, when you were just drinking a glass of water, ideally, is there ice in that? That is a question that I am really interested in. Hey, so good to see you, Dark Rules. Good to have you back. Polar Void does love ice and water. Polar Void, where do you tune in from? At some point I knew where you're based. Yeah, okay. There are so many different genders of ice out there. I actually really want. It's kind of silly, but I really want to get one of the pebble ice makers. That makes, like really, really crunchy ice. Okay, India right now. That's right. It's got to be, let's see, what time is it in India right now? Wow, 5:30 a.m. I am touched that you are awake at 5:30 a.m. to hang out with me. Cold water, never ice in water. Okay, Rat Cat, where are you from? Where are you tuning in from? Ooh, vintage ice crusher. That sounds incredible. I did used to have it was like a snow cone maker that was, you put just regular ice and it would shave it up for you. And that was a joy. I enjoyed that. Okay. I have heard that ice in water is like kind of a uniquely States thing. Although I imagine, like, I don't know. I think so often the States is just contrasted with like Europe, and it's like, oh yes, like in Europe, relatively uncommon to have ice in your water. Also, most places in Europe, most of the time, it's like kind of cold, so you wouldn't care. Like I imagine most places where it gets hot outside, people are like, yes, cold water would be better. But fair enough. Okay, cool. We're 4 minutes after the hour. When we get to part 3, I'm like, I'll introduce myself, but I don't know that anybody is here and hasn't already interacted. But hi, my name is Will. I am a software engineer at Google. I am also a coach at Major League Hacking. And importantly, I am a big fan of a library called SKlearn, which is going to be the big thing that we dive in today. I think today we'll do SKlearn, and then tomorrow we'll do TensorFlow and Keras, if you are following along. So let's get into it. Let's see, where is OBS? Boom. Okay, so here is our Kaggle competition that is sort of our home base all this week for this track. And then you can check in at this third link right here. Definitely check in. Speaking of checking in, let's check in with our leaderboard. So we have 14 teams, which is incredible, astounding, lovely. And okay, we have a little progress. No Moss coming up from behind with an error of 53,000. So remember, this is on average when you predict how much a house should cost. The this person got on average $53,000 away from the right answer. And remember, our average home costs about 300 grand, if I remember. So that's not terrible. That is telling you on average sort of what the ballpark error is. There's also an interesting thing with mean absolute error, which is this metric of on average, how wrong is your prediction or how far is your prediction from the right answer? Because the best you can do is 0, but the worst you can do is like technically infinity. You end up with this issue of sort of the outliers. Anybody from stats knows that the outliers can really yank a number out. And so if there are 1 or 2 that you got a ton of error on and everything else you got 0, then you would still see a relatively high number here. So I would say 53, that's looking pretty good. And lots of folks down here that both that have good levels of error and also a lot of unique scores, which I love to see. Sometimes you'll see Kaggle competitions where like every single notebook has the same score and you're like, yes, like someone published the results, which is cool. Love it when people share. And people have just submitted that, which no issue with that, but it's really cool to see that, there are 8 or 9 unique solutions that people have come up with, which is really cool. Good morning. 5 a.m. in Pakistan. Wow. I am again touched that you are on this early. That is great. Also, lots of folks from India. Yeah. Really, really great to have y'all. Okay. I used to do more like putting out a form at the end to ask, like, hey, what did you like? What could I do better? If you ever are like, hey, I would love sessions to be earlier or later, that's actually feedback that I'm super open to. If you like this kind of session and would like it to happen at a time that's more convenient to you, I guess for folks in India, maybe even just like an hour or 2 later might be nice. But right on. Okay, let's do a really quick recap and then we can get into it. So remember, if you come to our code tab right here, you can see all of the notebooks that we have. So these 4 are kind of the official ones that I have published that we'll be going through live on stream. But we have 2 that other folks have put out there, which are awesome. I love to see the number of comments on this one. There's really some engagement and discussion, which is great. So in part 1, we just reviewed Python. We got into some of the nitty gritty, which was really cool. It was very nerdy, relatively fast, as we say on this stream. Part 1.5 was just learning how to submit to this competition. And so you can see the score when you submit a notebook, you get a score on it. And then part 2 yesterday was diving into our actual data set and doing some exploratory data analysis. We looked at what our different values were, how we might want to clean some of them up. We looked at some that were just not super relevant or would be difficult to deal with. And then a big thing is we learned one way to deal with really 2 ways to deal with categorical variables. One of them was to do one-hot encoding, which is where instead of one categorical column, you end up with several binary columns of yes or no, it is in this category. And then we did the for states, because 50 states is just a lot to do a one-hot encoding for. We took the average house price per state and replaced the state column with average state house price, which was cool. So now we can jump into part 3, which is building a simple model. And I think that we will maybe start with just a quick definition of machine learning. Kaggle expert. Oh yeah, actually, okay, yeah, we'll re-hit the whole Kaggle progression thing. So you can upgrade from a Kaggle novice to a Kaggle contributor relatively easy. All you have to do is run a notebook, submit to a competition, upvote a comment, and comment on something, and then you become a contributor. It does get a little bit tougher to get to expert, but I think one of the easiest ways to get to expert, which is why I'm an expert, is when you publish a notebook. If you get 5 upvotes on that notebook, I think you only need 5. You only need to do that 5 times, and you become an expert. So yeah, publish your notebooks, I guess, is the moral of the story. So yeah, let's talk about machine learning. So I think especially in the past, year, 6 months to a year, I mean, really since the release of ChatGPT, machine learning and AI have really gotten thrown out there, and everybody is talking about these things, and they're being used a lot, right? These words are just showing up everywhere. Sometimes sort of like in ways that seem responsible and accurate, and sometimes not really at all, right? So I will throw out some sort of definitions according to Will that I think are actually pretty accurate to the really rigorous academic definitions. So generally speaking, artificial intelligence is just any time a computer or machine does something that seems intelligent, right? And there are like a million and one ways that a machine can seem intelligent, right? Like in a particular sense, a sorting algorithm is artificial intelligence because like sorting numbers, that feels like a thing that humans would be good at. And that requires intelligence. And if a computer can do that, that is it behaving intelligently artificially, right? And so that's like a really simple, broad definition. Under this, almost anything can be considered artificial intelligence. People will use the terms strong AI or general intelligence or general artificial intelligence. And this just kind of denotes some kind of strong sense in which this AI is really good at solving a wide range of problems. But that gets a little bit murkier. So AI, a really, really broad term. Machine learning gets a little bit more specific. And the definition that I think a lot of people use that I think is a good one is anytime a computer gets better at a particular task when it gets more experience. So the task and better and experience are kind of our three words we have questions about. But experience usually comes in the form of either additional data or additional time to do computation, right? So we think of the size of your data set and the amount of time you spent training. That's kind of what we mean when we talk about experience. And if you're curious about like, wait, what is time training? What is our data set size? We can dive more into that. But then you look at how well it does on some kind of task, right? And if it does better on that task when it gets more data or more experience, then we call that machine learning. If you have any questions, that's like a broad thing, but I think it's good to throw out to anchor in, like when we say we're going to build a machine learning model, what has to be true about that thing? Cool. Then we will now get rid of my head and punch back in. So we are on part 3 right here, and you should be able to click copy and edit so you can kind of follow along in real time. So this is just a copy of our last cell. If you remember at the very end of yesterday, we grabbed all of the prep work that we did and we stuck it in one cell and into this pre-process function. And the nice thing about that is now we can just copy and paste that into our new notebook and use that as like, yep, all our data cleaning is done. So if you run this, it'll take a second to boot up, but this will import our training and test data sets. We will build our average home prices by state little thing, and our convert lot area. So remember, some of our lot areas were in square feet and some of them were in acres. And so this just basically says if our lot area was in acres, multiply it by the number of feet in an acre. So we just get square feet. And then our pre-process does all of that pre-processing. We convert acres to square feet. We one-hot encode our home type. We merge in our average home prices by state so we can have a number there instead of a category. And then we drop some unnecessary columns. And so now when we call pre-process, we now have a clean training set and a clean test set. Okay, so we talked about what machine learning is, right? But so now we want to talk about what is a model. So we will talk, people throw out the idea of a machine learning model, right? ChatGPT is a machine learning model. And when we talk about a model, really, I mean, any simplified version of something is a model. There's like a broad definition of that. But in machine learning, our models usually look like a function. That is to say, they have some input and it predicts some output, right? So with chatbots, the input is the history of a conversation, and the output is what the next word should be, right? With a medical diagnostic tool, like, if you're trying to predict if someone has cancer, the input could be an X-ray of their chest, and the output could be the diagnosis. But for our challenge, the input is everything we know about a house, and the output is how much it sells for. So one of the simplest models that we actually already did was to get the average of all home prices and just always guess that number, right? So we could just say, okay, what is the average price? And yeah, it's a little over $300,000. And so you could just say, I'm going to guess that for everything. So we could just say in our training set, we're going to add a predicted column that is just that number, right? We just copy and pasted that number. Then we can go and calculate mean absolute error. So if you remember, we talked about the idea of the mean absolute error is how far away are you from the right answer. on average, right? And so we can calculate that really pretty easily by saying, so we can get an absolute error column by subtracting our predicted price from the actual price and then taking the absolute value. So that's our absolute error. And you can see if we scroll over our absolute error, okay, because the let's see, the actual price was 3,000 or 358,000, and our predicted was 338,000, and so our error ends up being 19,000, right? That's just the distance between the actual thing and our prediction. So then to get our mean absolute error, we just take all of those things we predicted and just take the mean of them, right? All of the differences, and we just do a mean. So this gets us down to 142,000. And we can actually plot a histogram here. So some of these things have, in a lot of cases, we actually get kind of close, right? Like relatively low amounts of error. And then there are some things that we have really, really high error on. But so our average error ends up being $142,000 and some change. So this is, technically this is a model, right? And in some sense, it's a machine learning model, because if we got more data, you would expect our average to get more accurate. At some point, you really are not. It's not clear how much. At what point you would stop getting better, right? Because just getting closer to the mean, you'd have really, really diminishing marginal returns. But this is it predicts a value, and it does that based on the information it has, right? Which I think we already did this. We already, or I think we just predicted that everything was $100,000, which I think had an even worse error. Cool. So now I want to propose, we're going to do one sort of very dumb model that should be really easy to understand, that should improve our performance. And then we'll learn about sort of some of the drawbacks of machine learning. And then we'll learn about a library that sort of does all of the nitty-gritty stuff for us. So I say houses that have more square feet of livable area should cost more. Right? I think this is just general intuition. And we know from our exploratory data analysis that the square footage of a house is I think it's the single thing that correlates most closely with the price, right? As you add an additional square foot, the price of that house usually goes up. So one model that I could propose is, let's just find the average price per square foot. So, take if a $100 house has 100 square feet, then that's $1 per square foot. Let's find that number for our entire data set. And then once we have the average price per square foot, then we can just say, when we see a new house, take whatever the square footage of that house is, multiply it by the average price per square foot, and that gives us a prediction, right? And so now this finally gives us a prediction that's different for every house, right? It's not just one guess for everything, which is, obviously a bad model. But it'll get us hopefully a little bit closer to something intelligent. So we can take our clean training data set, make a copy of it. And then right here, all we're doing is we're taking the price and dividing it by the living area. So this is how many dollars for every square foot. And then we're just going to take the average of that. So across all of our houses, on average, how many dollars do you have to pay for a square foot? If we run that, 195. Okay, so on average, if you want an additional square foot in your house, you have to pay $195. I think this is for me, it's like a mind-bendy thing about I look at my townhome and I'm like, oh yeah, that square foot over there, that's a couple $100. That's wild, because how bad do I need that square foot? Do I need it, do I need it $300 bad? I don't know. But so that is our average price per square foot. Let's see. With the square footage model, could it be a more predictable model because that's how house for sale listings are presented, price per square foot, or is that not a relevant correlation? Oh, okay. So that's an interesting point. If I'm interpreting what you're saying, you're saying that specifically because that information is known to the buyer, it's you're going to see that information and it's going to influence maybe how much you're willing to pay. And I think that's totally I think that's good, a totally valid thing to sort of build into our intuition here, right? Why should this be true? And yeah, even if the market is, is doing its thing, most people would have a hard time spending $1 million for a 200 square foot place. Cause wait, $1 million for 200 square feet, that's like $5,000 per square feet or whatever. And so, yeah, I think this intuition about like, well, people see that number when a listing is up is totally valid. Okay, so we have our average price per square foot. And this is what we're going to call a parameter. So our model right now has one single parameter that we have tuned, and we have picked this number 195 as the best number we have for the average price of a square footage of livable space. So now, instead of just assigning one number to our predicted column, we can actually take the entire living area column and multiply it by 195. So now we have our predictions here, and we can do that same calculation to see how far off our model is. We have our predicted and our price. So, wow. Okay, so I'm going to scroll back up. Our original error was 142,000. And just by changing the way we do our model, we dropped down 108 to 118,000. Now, this is an incredibly simple model, right? Like we're going to get to stuff that's way more powerful than this. But a jump of $20,000 in error, like that's pretty good. Just by switching from just a single mean for everything to actually multiplying the average price per square foot with our living area. Now, what we have just done is a simple version of a machine learning algorithm called linear regression. The idea behind linear regression is just this, is you find the average thing that you should multiply a value by in order to get your output, right? Now, we just looked at it with one variable, right? We did univariate linear regression. But to make it more powerful, we can think about adding lots of variables in there, which we'll look at a little bit later. So for example, you could imagine living area, but also number of bathrooms and number of bedrooms, right? I almost feel like square footage, bedrooms and bathrooms are kind of like our holy trinity of like, these super relevant things that everybody wants to know about the house. That gets a little bit tougher for us to do manually. And so that is where Scikitlearn comes in. So Scikitlearn is a really, really cool library. In fact, I will pull it up. I will say if you are getting started in machine learning, Scikitlearn is going to be like one of the most valuable tools for you. So it has really, really good documentation, lots of cool visualizations of what the algorithms are doing, which I think is really neat. And the sort of basis of it is that a lot of algorithms that you could implement yourself are sort of implemented for free, right? We talked about this idea of like, oh yeah, you have your own book of recipes, but what if you could just go to the library and check out somebody else's book of recipes? And that is essentially what Scikitlearn is. It is a giant recipe book of machine learning algorithms that you can just borrow. So for linear regressions, we will say from sklearn.linear model. So linear regression is a linear model, and import linear regression. It sounds so close to Scikitlearn. Yeah, well, and in many ways, Scikitlearn kind of is a sidekick to to TensorFlow or to Hugging Face or to all these other bigger. I guess the other thing that I should put out there is that there are more powerful libraries. I think Scikitlearn is powerful for how simple and easy to use it is, but there definitely are sort of bigger and badder libraries out there, and we will look at one of them tomorrow if you're interested. Cool. So we import linear regression, and this is the class that is going to do our algorithm for us. In a sense, this is our model right here. We can copy our clean training data into a linear regression data frame. And here we are going to instantiate our model. So this is basically, we're asking Scikitlearn, can you make a linear regression model for me? And it will whip it up and it'll plop it out here. This is a really long name. I guess it's really descriptive, but I'm going to change, if everybody's okay with it, I'm going to change linear regression to linreg. Cool. So now we have to get our input data and our output data. So our input data, we're just going to use living area just to match what we did up above. So we did it kind of manually, but now I want to show you how you can do basically the same thing with Scikitlearn. And then our output data. Now, here is a minor thing. So we have our linreg df. You notice I have two square brackets in here. If I remove them, you end up with, I just have to run this, don't I? If I remove them, you end up with a series. But if you have those second set of square brackets in there, because that now means you're indexing with a list, the thing you actually get is now it's a data frame with a single column. And this is sort of a silly distinction, but technically that first thing was one-dimensional, and this is actually two-dimensional. It just happens to have a width of 1. If that's a little bit weird, that's okay. The technical math words for this is a matrix, but if it's only a single line and it's one dimension, then that is called a vector. So we will get our input data, which is a matrix, which is why we use the double square brackets. And then our output data can be a vector. Our output data is just a single line of numbers, and that is our price. So now we have our model, which I'll update to the new name that's a little bit shorter. And we can call fit on it. So fit is sort of this magic function on Scikit-Learn models where you give it all of your input data and your output data, and it will do training to figure out what the best set of parameters are. So remember, up here, we manually calculated what the price per square foot was. But linear regression, our linear regression model will do that automatically for us. So you see we get a linear regression model out. And now if we want to test it, just like we did earlier, we can just call predict on our input data. So this is going to give us a set of predictions for all of our inputs. And then we can, like normal, get our mean absolute value, or mean absolute error. Oh, yeah, we need to use that new name again. Teehee. Boom. Okay, so we get even a little bit smaller. We have $110,000 of error. So you might ask, wait, hey, Will, if you said we're doing the same thing, and here we got $118,000 of error, and here we only get 110, like, why did it improve? And the answer is kind of simple. With technical linear regression, you have coefficients and what's called a bias or an intercept, which is, if you remember from algebra, your sort of technical definition for a line will often say y equals mx plus b. And when we were doing it up above, so our x here is square footage, and then our m was average price per square foot, and we're multiplying those together. But we didn't actually include any constant here. We basically just said this is 0. And that means that it's not going to be as good of a line as if we actually picked these numbers a little bit more carefully and included an intercept or a constant or a bias or whatever you want to call it. And so because our model here can really easily do that math for us, it gets a little bit better to the right answer. Okay, here's a great question. Must all your vectorized features have the same length? In a word, I will say yes. So generally speaking, the thing that we put in is just going to be a set of numbers, right? So in this case, our set of numbers is just living area, right? And you could add another column, but you would then need to add another column for everything, right? So you can see why this would be a sort of propose a difficulty if we wanted to put a string in here, right? You can like technically imagine that your model could try to make sense of an input of a string if you just converted it into numbers. But like technically the way you'd have to do that is you'd have to have like a column for every character. And if their strings aren't all the same size, there are tricks you can do. You can use padding. So, make everything 1,000 characters long and then just put zeros where there are no characters. So just, put a padding of a bunch of spaces. But yeah, generally all of our inputs here need to be the same length. You can get into sort of more complex models that can deal with variable lengths of things, but that definitely gets, a little bit more advanced. Yeah, great question. I love variable names that are so long and they would absolutely not show up on old versions of Windows and such. Yeah. Yes, you can. Okay, Polaroid asks, can we see these coefficients after training? Yeah, that's actually a great question. So we came up with the average we came up with the average $195 per square foot. So I believe, let's see, actually, let's do this the old-fashioned way. There is an internal, let's see, there is, I think it is coefficient, yeah. And then I believe there is intercept as well. Intercept, so coefficient and intercept will give us our numbers there. So we can do dot coefficient, and then dot intercept. So what is this telling us? I want to actually try to get an intuitive understanding here because I think this is super interesting. So this model did better, and it's, essentially its price per square foot is $134. And then its intercept is 90,000. So essentially what this model is saying is, hey, on average, just having a house, any house, is worth $90,000, right? Just to have any house is worth $90,000. And then every square foot you add to that house, that's just kind of gravy, but each square foot only really gains you $134 in value. So those are the coefficients, or those are the parameters that it picked. So we've now gone for a model. Our original model really only had one parameter, which was the average average price per square foot. And then down here, we actually have two parameters. One is the price per square foot, and this one is the price for having a house at all. Yeah, Polar Void, really astute observation. Your 0 square foot house is worth 90,000. Now you might ask, like, wait, isn't that weird, Will? Like, isn't this obviously laughable because this would say that a 0 square foot house would be $90,000? And the answer is yes and no. So because there are not that many houses that have that few square feet, this actually ends up being relatively accurate on things that are normal, right? So yeah, if there was a house that had 0 square feet in it in our data set, our model would do badly on that. That just isn't that common. And so our model decides basically, yeah, I don't need to worry as much about that specific case, just because it doesn't happen a lot. Cool. So we looked at our coefficients, and we looked at our average error. Okay, so another thing that we've been doing ourselves, so we picked our own parameter and calculated it ourselves, and then we did that automatically. We've also been manually calculating our mean absolute error, but there's also just a function we can use from that. So we looked at SKlearn linear models, but another module inside SKlearn is called metrics. And so a lot of the metrics that we'll be using really for this Global Hack Week and in the future are in sklearn.metrics. So mean absolute error is a sort of classic example, or the classic example that we're using this week. And so you can, instead of doing your own math, you can just call mean absolute error on your predicted values and on your actual values. And you can see we basically get the exact, no, not basically, we literally get the exact same number. So that's great. We were doing our calculation correctly. Okay, so we've talked about how this model is linear, right? And on some level, that means that the only kind of line it will draw is a straight line, right? And we've talked about how, hey, some of these relationships aren't exactly linear, right? If we actually, if we go back to part 2, we can see, I think we did plot square feet by price at some point. I think it was at the very end when we were doing sort of fun visualizations. Maybe it was further up. Okay, here it was. And so you could see, yeah, like there are houses all over the place, right? There's, any kind of house you want, you can find. But we saw the denser area here. It kind of does a little bit of a curve, right? That yeah, if you're not that many square feet, you're usually pretty cheap. But then as you gain square feet, it doesn't really go in a straight line. It kind of comes up in curves. And it's like not far from a straight line. But you might imagine that a curve would be a better line to fit, right? And our linear regression model, under the hood, it's not going to do that. But if we want to get a sense of what that sort of should look like, then we can actually generate our own variables, right? This is sort of another way of feature engineering where before we feed it to the model, we can just say, well, hey, what about living area squared? What about the square root of living area? So remember, star is how we do exponents in Python. And so if you do exponent 2, that's squaring it. And if you do exponent 0.5, you're taking the square root. So we can define 2 new values, living area squared and living area rooted. And then this is the thing that's really nice about SKlearn. I mean, there are many things that are really nice about SKlearn. But once you have a model down, you can just iterate really quickly on what different kinds of inputs you want to put in there. So we could include living area squared, and living area rooted, and we still just want to predict price. So we can do the same fit function, but now on slightly different data. I think, is this, Oh yeah, this is, we still want to call this linreg, don't we? And if we run this, we would expect, hopefully, to get a slightly better performance. And if you look over here, it's like, well, it's roughly straight. So like maybe we won't do much better, but maybe we will. Well, that's unfortunate. We technically do a little bit worse, which I don't have a great answer for why we would do a little bit worse. Which I think I already knew this was going to be a little bit worse. So maybe I should have picked a better example. Yeah, this is a second order equation now. Yeah, because we have a square in there. We fit our input and output data. Yeah, so we did a little bit worse. It's really pretty close. But hey, maybe we just didn't include enough factors, right? Maybe we should include something with squared and cubed. And in fact, we could try right here. We could just add a cubed. Living area cubed. And see if that gets us any better. Okay, cool. That actually does improve it. We do actually end up getting a better performance by a decent bit. We're $50 closer to the right number on average. And so what we're doing here is on some level we're giving our model more capacity, right? Because for every input variable we give it, it gets another parameter. And so if you have heard the parameter count of ChatGPT is 100 billion or something like that. We're in kind of the big models are now sort of tens to hundreds of billions. And so what we have done is we've gone from 4 parameters to 5 parameters, right? So ChatGPT is up there at 100 billion, but now we're at like 5 parameters. And so we are adding sort of more neurons to our little artificial brain, kind of. And so we got a little bit better, right? So you could say, hey, this is great. Why don't we do this again and again, right? So I now have a list where we have our columns, but we can actually just in a loop say, hey, raise it to the power of 2, raise it to the power of 3, raise it to the power of 4, and so on and so forth. And we can get, hopefully, because we're making our model bigger and more powerful, we should get better performance, right? So this is basically doing the same thing we did up here, except now we have all the way to, let's go all the way to 6. Let's get our power of 6 there. So I want everybody to take a guess in your head. What will our performance be? We used to be at 110,750 of error. Then we dropped down to 110,700 with no 50. And now as we add a bunch more parameters, how much better will we get? Make your little guess in your head or in the chat. If anybody guesses and gets it right, then that would be great. And okay, we actually, oh, that's unfortunate. We actually go up, which this actually might be, no, this actually should be fine. We do still have living area rooted. But yeah, so we don't actually improve much. In fact, it looks like we get a little bit worse, which would be an interesting, there's like a separate deep dive here of just like, well, hey, why did it get worse? But hey, maybe we just didn't add enough parameters, right? But you might ask, hey, why is it still bad? And in order to explain this, I want to turn to some fake data for a second, because this data is relatively complex, but I want some data that's really, really simple to demonstrate a specific point called overfitting. Somebody asked if I finish this project, would it be helpful to put on my resume for transferring colleges? Yeah, I mean, personally, I think that this kind of project is super, super great to put on your resume, because this is a really, it's a really tangible problem that, people solve all the time, or people need solved all the time. And I think it's really neat to say, yeah, I took some real data and built a real model around it. I would certainly encourage it, especially if you are, if you are transferring into a computer science department or, or math or machine learning. Okay, this is actually a great question. And this is something I should call out, is that really I'm not doing great here, or I'm not doing something that I should be doing here, which is using a random seed. So when it is trying to figure out what these numbers are, the way it does it basically is it takes it starts with random numbers and then it slowly tweaks them to try to find better numbers, right? And usually you basically get to the same place, right? Usually as you slowly tweak your numbers to try to find the right one, this kind of gets into gradient descent, if you've ever heard this, or stochastic gradient descent. There's a little bit of randomness in that system. And so something that you will usually do if you are experimenting and you want everybody to kind of be on the same page is you will use a random seed that everybody shares to make all of your like random things that happen. Like they'll still be random, but they'll be the same random for you and me. So if, for example, one thing we could do is we're creating another linear regression model here. I could say, I think it's random state equals 0. But not expect random state. Let's go and check our model and see if we can override the random state. Maybe we just need to seed random before. Okay, maybe it's not on the model. Bear with me here just for a second. SKlearn seed random state. Cool, this seems right. Okay, it looks like they just use the NumPy random, and so we can seed NumPy's random. I don't want to get too deep into random number generators, but the long and short of it is that when you start from a certain random seed, if we all do the same things after that, then we should all get the same result. So if I just said, do we already import NumPy? If I seed it as 0, and if you do this as well, and then you run it, oh yeah, we need to take our random state. Then you should get the same result as me. But if we do change this, it's possible. I would expect not always, but it is possible that we would get another, like a different result. Yeah, we're getting. Oh, that is my best guess as to what's going on. Okay, so Polar Void says, well, I'm a little confused. Isn't all of it dependent on area? Doesn't that make them not really different features? Yeah, so this is a great question/point. So on some level, you might guess, yeah, the information that we're getting from this should all be captured. And this comes down to when you are using a given model, you need to think about what kinds of relationships can that model capture. So when you use like a really big, beefy neural network, there are basically no kinds of relationships that it can't capture. Like pretty much any relationship in your data, it at least has the ability to capture, because it's, you can make a neural net big enough to be functionally Turing complete. When it comes to these simpler models, they all have really specific limitations. And so linear regression can only model a relationship that is linear, right? So okay, this is a little bit of a digression, but what are we here to do? What if I got a list of numbers? Let's see. Actually, let's be good about this and create a little header here. A digression into linear models. Boom. Okay, so let's get some linear data. So if I said x is equal to list range 0 to, we're going to just say 100. And then y is equal to, let's see, we'll call it xi times 2. And then, so if we just print out x and y, oh, sorry, for xi in x. This is just called a list comprehension, but it's basically saying take all of our numbers in x and multiply them by 2. If that's confusing, don't worry about it too much. So we have a long list of maybe 100 is too much. Maybe we just say 1 to 20. So we have 0 through 19 and then 0 through 38, right? Because we just take whatever our x is and multiply it by 2. Now, if we graph this, we can plot x versus y, and we get a nice sort of linear, linear. I mean, it's a line, right? It's just a straight line. Now, if we made a linear regression model that say, so let's say linear regression, and we'll just call this one ligreg. And if we fit linreg on we can input just X as our input data, and then just Y as our output data, and fit. Oh, let's see, will that run? No, we get errors. Oh, maybe we can take this out. No. Okay, apologies. Maybe we actually want to make these a NumPy array just for simplicity. A NumPy array is just a simpler thing. In fact, actually, if we make it a NumPy array, then we can just say X times 2. And that still works. And then will this work? Let's see if I want to change the shape. T-shape. And if I want to change it to 1 by 20. Oh, come on. Inconsistent number of samples. What am I doing wrong here? Fit input data, output data, X and Y. I'm trying to prove or trying to demonstrate a really simple point. So part of me feels like this is silly. I actually think I do something similar down below. Okay, you know what? Maybe this will be easier in a data frame. Okay, so what if we just say data frame, and we say X is equal to X and Y is Y. And so we can say df.x and df.y. And that works. And then we can say linear regression. The input is X and the output is Y. Cool. So now I just want to predict based on X. And we'll call this linear predictions. And so now I just want to graph our predictions based on our linear regression model. dfx compared to df linear predictions. So our predictions are really exactly the same as the actual data, right? Our error here is 0, right? Because linear regression can model a linear, like a line perfectly, right? Because the only pattern it's going to produce is a line. But so now, what if instead of y being this linear just x times 2, what if instead it was x to the power of 2? So we graph this, you will see this is no longer a straight line, right? This is a curve. So now I want to do the exact same thing where we try to model this with linear regression, even though we know our underlying pattern is not linear. This is non-linear prediction. And then I actually now want to plot sort of the right answer alongside our predictions. So you can see our actual data is this curve, but our model is still only able to predict this straight line, right? And so this is because our model just in the internal workings of our model, it just doesn't have any notion of an exponent. And so even though there is just one thing going on here, which is a pretty simple function, our linear regression model will never be able to capture it unless we give it sort of the specifics of of what a square is or what a square root is. That was a pretty long digression, but I think it's kind of helpful. I don't know if that makes sense. But so to port this back to our square footage, in some ways, square footage might be linear, but in some ways it might be kind of more like a square root or more like a quadratic. And so by putting those numbers into our model like that, we might guess that we could get slightly better performance. But of course, up to a point. So I'm going to turn to some fake data here. And this fake data was picked specifically by me for this example. And here is our example. So this is, if we were drawing a line here, is to like you'd imagine drawing something a little bit curvy, right? This almost looks like a square root, right? But there are a couple data points that don't really fit it. And this is really common in machine learning. You have a data set and there's a general trend, but there are definitely some weird data points, right? If we come back here, it's like, yeah, there's a general trend here, but then there are these guys out here. Like, what are they doing, right? And our model needs to decide what to do when it sees that sort of outlier. Another kind of detour. The best way to improve accuracy on Kaggle is to put the work in on the data, get rid of outliers, etc. Yeah, so this is definitely, this was part two yesterday, was sort of the trying to clean things, trying to make sure that our values made sense, removing outliers, etc. So yeah, excellent point. And that was yesterday. And so definitely, if you haven't seen part two, go back and check it out. And I should call out that even yesterday, there were a lot of things we didn't get to, right? There are, still some of the other categorical variables. I think we threw away zip code and we threw away city, but you could imagine doing the same thing, either one-hot encoding those things, or you could imagine doing what we did with state, where you find what's the average price of a house in this zip code? What's the average price of a house in this city? And that could potentially be helpful. So we have a pretty basic pattern here, but not everybody fits it perfectly, right? So what I want to do now is, this might seem a little bit crazy, but I'm going to go through 1 to 40. So we are going to check raising it to the power of 1, raising it to the power of 2, raising it to the power of 3, all the way to the power of 40. And so these columns will, at each step, have even more of these variables. So we're going to build 40 different models. And then we're going to predict all of put all of those predictions into a column, or into a list here. That was pretty quick because Scikitlearn is pretty fast and linear regression doesn't take that much compute power. Which I don't know if anybody has a question about like what's going on here. I'm happy to sort of walk through this line by line. But we're just saying from 1 to 40, compute from x to the power of whatever that is, and append that column. And then for the fake data, actually create a column that is the fake data raised to the fake x raised to that power. So we will get, our fake x to the power of 3 and to the power of 10 and to the power of 40, or 39 technically is where we max out. And then we actually make a model from that, fit our data as best we can, and then store our predictions so we can look at them. So then I just grabbed a few. We'll look at predicted from a single parameter, predicted from 2 parameters, predicted from 3 parameters, from 9, and then all the way up to 39, sort of our biggest model. And we'll just plot all of those. So just like we saw before with our little digression, our linear model could only do a straight line. And so it really doesn't capture this that well. I mean, it could be worse, right? There's a certain kind of linearity here, but it's not, it's really better described by something that has a little bit of curve to it, right? Okay, so now what if we have 2? I would say this is a little bit better, probably. It gets a little bit closer to a lot of these. It does have quite a bit of error on this last point here. Even down here, it has quite a bit of error. So, far from perfect, but I would say this is a better fit. Here, okay, I could see this one as well. If we have 5 variables, we're still pretty close to most of them. It kind of gets a little bit closer on this guy, but it's passing through several points. So maybe this is still reasonable. It kind of seems a little bit like overly wobbly, but I could imagine this not being crazy. And then we get to predicted from 9, and suddenly things start to feel a little bit wacky, right? It does get closer to more points, but this doesn't really look like a trend, right? This looks like we're sort of reading tea leaves and, and just drawing a zigzag line to try to touch as many points as we can. And then finally predicted from 39. And okay, with some weirdness here at the beginning, but after that, we're just connecting the dots, right? And you could say, like, hey, isn't connecting the dots helpful? Like, we're matching all of our data. And this is what's called, so in all these cases, we're trying to fit a line to our data. And this is what is classically called overfitting, right? And the way to think about this is if you come back just to our original data, like we really, I mean, humans kind of look at this and they kind of draw a line and they notice that two of these are kind of not normal data points, and they kind of try to fit the main thrust of the data. But if we come back down here, like what is, if we tried to guess like, well, what should a like 2.9 be? And if you just had your, I was about to draw with my finger on the screen, but I realized you wouldn't see that. If we just draw our arc right here, then 2.9 would be about here, right? But our model right now, if we just asked it, well, what value is 2.9 at? It would go all the way up here. And so that difference there is pretty big because it's saying, well, there's this one data point up here and I have to fit it. And yeah, A. Jackson said, so this is overtrained and it's not generalizing properly. Exactly, like hit the nail perfectly on the head. And that is sort of exactly what's going on under the hood here. Polaroid, I'm thrilled to hear that you enjoyed this part. I feel like generally when you come to these streams, you're not hearing anything you don't know. But I think it can be fun to just revisualize things. You know, always a good time. So how do we prevent this? Well, one thing you could say is, yeah, it was kind of a silly idea to include, you know, x to the power of 40 in our equation. So maybe just don't do that. And for starters, that's, you know, I think generally a pretty good thing to do. But another issue that we had is that we were testing our data on the same data that we were training on, right? And so this is the actually one of my favorite descriptions of this comes from Polaroid, which is that when you have when you are testing on the same data you're training on and you can just memorize things, that your brain can kind of, or your machine learning model can kind of get into conspiracy theory mode. It can start seeing patterns that aren't actually there, right? Like this right here, this is a pattern that I would say doesn't really exist, but if you squint hard enough, you can say, oh yes, like every time it's exactly 3 on a Tuesday, this is exactly the number, right? And fundamentally, that generalizes poorly because it did not actually capture the generalizable pattern in our data. So one thing we can do about this is don't test your model on data that it's already seen. So we can take a moment and split out so we can grab our living area and price, still just using this one variable, and we can call it x and y. And then from SKlearn, another helpful tool in the toolbox is called train test split. So sklearn.model selection, train test split, just splits a data set up for you so you have a portion to train on and test on. Now, this can get a little bit confusing because train test split is like we already have a train set and a test set, but we're basically going to break our training set up into our own little mini test set. That we already have the answers for. Sometimes people will call this a validation set that I think actually might be a little bit clearer, but we use train and test here. So another thing that you can do is instead of just doing this once, you can randomly change the split of your training and test data so that there is some random chance that things show up in your test set. So you're not just getting one test set, you're getting 4 different test sets. So that's what we do in a loop 4 times. We will split our train and test set up. So we pass in our x and y and our test size. So this says 20% of our data will end up in our test set. And then random state, we're just making it random so that we don't get the same split every single time. Then we'll build our linear regression model. We will fit it. We'll make our predictions. And then we can append the amount of absolute error we get to a list. And so as this runs, oh yeah, I guess it's really fast. We can see every time we build a new model with a different split, we get slightly different errors, right? There's a time where we get 108, we get 11 or 110, 110 again, 110, but all these are a little bit different. So our average error, when we look across all of these cases, like on average, how well does this model do on stuff it hasn't seen before? And it is about $10,000 or $109,000 of error, really closer to $110,000 of error. So this gives us a lot more confidence that what we're doing is going to generalize by testing the model on data that it has not seen before. Any questions on that? This is, I think this is sort of like the most, if there's sort of like a foundation of machine learning as a science, stuff like this, sort of doing a cross-fold validation is what this is called, and avoiding overfitting. This is really, really into the heart of machine learning as a discipline. Hello, Tintin. Good to see you. Welcome, welcome. Cool. So now instead of just using living area, our X here will be not just living area, it will be everything except for price. So basically all of our data. So we can just drop price. And if we just double check what's inside here, because it's been a minute since we've looked at this. So we're left with ID, bathrooms, bedrooms, living area, lot area, our one hot encoding, and the average state price. So this is now a lot more data that we have going on. So now another moment to take a guess in your head. We were around $110,000 of error. Now that we're throwing all of our data at it, what do we think we can get? I think it's totally possible that we could get under 100. 80K seems reasonable. I don't know if we'd get as low as as like a 50 or 60K. But yeah, I'm gonna guess maybe 70 to 80K of error. Hey, look at that! Look at that! So at some point I did know this, but I definitely forgot, and we're pretty close to about $70,000 of error. And this is the only thing we changed here is we just included all of the columns that we had cleaned. So that's looking pretty good. So now what I want to do is I want to actually turn this into a submission. So if you go back and you come back to the competition, let's see. There we go. You can find under code our submitting. And this is a nice demonstration that you can copy and paste from just for how you should, like what the format of your submission should be. So we need a column that is price and ID. So we can grab our test set. So I think it's called clean test. We want to generate predictions for this. So because this doesn't actually have any price column, we should just be able to pass it directly in to our model. So our most recent model, we can just do model predict on this whole thing. And we get an array of prices. So we can say clean test price. And we can say submission equals clean test ID. And add a submission.price. Oh yeah, it's upset that we didn't make a copy, so we can make a copy. The submission should just have an ID and a price, which looks good. And then down here, all we have to do is write it to a CSV file and drop the index, because pandas for free will give you this index. So we can write this to a CSV submission, and then we should be able to just submit. So we'll click submit, and there are a few other ways we could try to power this up. Oh yes, I will share the Kaggle link. Let's see. Boom. Oh, Polaroid beat me to it. Let's see. Would doing OHE on the states be too much? I'm assuming the distribution may vary drastically in certain states. What does OHE stand for? OHE. OHE, machine learning. Oh, one hot encoding. That's what it stands for. Yeah, this is a good question. So yesterday I threw out this rule of thumb that around 10 tends to be like a decent threshold for if you have more than 10 things in a category. No, yeah, I'm sure OHE is accepted acronym for one hot encoding. I just wasn't thinking about it. But around 10 and you start to run into some problems. Usually this actually comes down to this idea of overfitting, that when you have more columns than you have rows, or when the number of columns you have gets pretty close to the number of rows you have, you can think about it for every row or for every column, you're going to have a parameter. And so for every column, you're going to have a parameter. And so that's making your model bigger. And so if you don't have enough rows to sort of give you generalizable power over those columns, then it can cause some issues. So I threw out 10. That's not like a, I mean, it's certainly something you could try. I actually was thinking after we submit this, if it works, it did not complete. Let's debug something. I was thinking we could maybe even get the average state or the average zip code price and the average city price. Oh, that's not what I wanted. Oh, it failed. Okay, yeah, let's get the logs. This is good because I feel like a lot of people will submit and it'll error out, and it's like, wait, how do I debug this? So you come over here, click on the thing that says failed, and then you should have some logs from when it ran, which it's very possible that I just didn't clean up one of my errors from above. linregdf is not defined in cell 7. This is, again, one of the problems when you are sort of iterating at the same time in the same file that you're submitting. You have to be careful that you are not leaving little straggler issues behind. But let's see, linreg in cell 7. It said linregdf living area. linregdf is not defined. Oh, did I do this out of order? Yeah, okay. I copied this from below and pasted it up above, so we can just delete that cell. Cool. Maybe we try submitting it again. And I believe some good news is that when your model fails to submit, it doesn't count towards your submission limit. Because in this competition, you get to submit 10 times a day. And now we wait. And maybe while we wait, we can talk about, so we come back up to all that stuff we copied from day 2 where we were doing our cleaning. In this, we throw away zip code and city, right? Now I'm just thinking about address, and I'm thinking about how some addresses have like cool names and some have like kind of silly sounding names, and how like probably like you could actually build a model that tries to figure out, does this address sound cool? Because on average, people will pay a little bit more for an address that sounds cool. Or even more, actually, something you could say is like there are different things that like the name of a street actually tell you something about it sometimes. So for example, like an avenue usually is like a large street in a city, whereas a court is usually a small street that has a cul-de-sac that's like a little bit away from the traffic. Probably not going to get to that in this live stream or this week. But zip code and city, we could have kept, right? So we could either one-hot encode them, or we could do this thing where we get the average home price by state and then join. And I like this idea just because it scales a little bit better. We're only adding one column as opposed to adding for city. I mean, let's check how many cities are there. We can grab our training data set and get city and then do unique and then get the length of that. So this should tell us how many unique cities we have. Yeah, we have 4,329 unique cities. And so this would mean we're adding 4,329 columns to our data set, which would be really, really aggressive. So instead, we can grab the average price per city, which we can basically copy and paste from this. We can say average home prices by city and just group by city. Easy. And then down here, this will be a little bit messy. I guess we can just copy this whole thing. Yeah, I guess we'll copy this whole thing. So now, instead of merging on state, we will merge by city on city and no longer remove city. And then we'll just call this average city price. But all the rest of this, I think, should be the same. We want that to be average city price as well. Oh, an error. Oh, I just misspelled city. Great. Teehee. Yeah, y'all got it. Y'all got it. Okay, yeah. Global hack weak points to Shemery and to Nanotubular and to Polaroid. Anudian asked, any prizes for the participants in the cow competition? Yes, actually. Great little intermission that I'll do to talk about prizes, and then we'll see after I fix my typo. So there are 3 ways that you can win a prize today or this week. No, not 3, 5. So number 1, if you are first place on the leaderboard, then you get a prize. If you are second place on the leaderboard, then you get a prize. These are all swag drops. We'll swag drop you. If you are if you submit at all, I will randomly select someone from all the submissions to get a prize. I might actually limit it to people that are contributors. So if you want to be in the raffle, try to get to be a contributor just by leaving a comment and upvoting something. And then the other 2 ways, so those are 3 ways that are all just based on submitting. The other 2 ways are if you have the best notebook that you share, so the best code contribution. This is actually, you have to publish it publicly, and I'll look at it. And then the last one is discussion. If you have a really, really good question or you answer a question really well in the discussion section, then I will just go through and pick someone to win that. So there are 5 ways to win prizes. And they are all swag drops, like soup. Yeah, there's been a lot of conversation about soup this Global Hack Week and whether or not coffee counts as soup. Okay, maybe I fixed my problem. So let's see. Does Clean Train now have, if we scroll over, average city price? Boom, love that. Okay, so this is kind of cool. You can kind of look through and see, this is a good example where the average state price is lower. It's like almost 300,000. But the actual price is closer to 400,000. But if you look at the average city price, that's much higher as well. So, thank you for calling that out. I like to go on tirades with my big face, and then I forget. We have now another column that is average city price, and you can see there are cases where the state price isn't really indicative of the actual price, but the city price is, right? And so it's powerful to be able to use these numbers sort of together. And then, let's check back in. Did our submission? Our submission did complete. Let's see. How did we do? We did better. $67,000 of error. So that is a massive improvement on our previous submissions. Right on. So if you copy and paste this notebook that I'll republish in a second, you could jump relatively high on the leaderboard. But now let's see, after we add our information about city, and why don't we just go ahead and add our information about zip code as well. So we can do basically the same thing with zip code, where we get the average price in your zip code. Let's see. We can copy and paste this again. Let's actually add some comments because this is getting a little bit intense. Add average price per state. Add average price per city. And then finally, we'll say add average price per zip code. So we will join on zip code. We actually need to go and make our average price by zip code dictionary or table or whatever. So we can say by zip code. We can group by zip code. And then back down here, we'll just find everywhere where we said city and change it to zip code. There's, I'm sure, a more elegant way of doing this, but it's quick and dirty. Boom. Oh, we got an error. Did I not join on the right thing? Key error zip code. Oh, zip code. I think it is just zip code. Oh, this shouldn't be. This should be by zip code. And we get average zip code price. Oh yeah, Polaroid, excellent, excellent point. We actually do want to be dropping these. So by all the things that we're grouping by and adding the average price, we should add to our final drop here. Yeah, totally a good catch there. As I like to say, it wouldn't be Global Hack Week if Polaroid didn't call out a bug that I had. No shade, no shade. I appreciate it. Cool. So now our data frame is back to all numbers, and we have all these additional kinds of prices, which are hopefully increasingly helpful. Although it is interesting to see that in a lot of cases, our average city price is the same as our average zip code price, which would be, I mean, the reason this would happen is if the entire city is in just one zip code, right? So you might guess that adding average zip code price is not as helpful. But of course, you can see, I mean, like in this case, the average city price is high and the zip code price is lower, and the average zip code price is actually closer to the home price itself. Cool. Now there was, and this really we're getting deep into feature engineering where there are lots of things that we could think about, right? So like you could even think about what's the average price per square foot in your city? What's the average price per square foot in your zip code, right? There are like so many different numbers that you could think of that might be helpful that you could add in there, and it's just this balancing act of it's overfitting as the danger, and the more columns you add, the slightly more likely you are to overfit. But this seems pretty reasonable. Now we've used basically all of our columns except for home status, date sold, and address, which seems pretty reasonable. So now that we have a new preprocess function and we have new clean data, what if we just went down to the very bottom here after all of our digressions and we do our cross-fold validation? So we were getting around $110,000 of error. And here, oh, that's just with living area. We want to use everything. No, yeah, we were getting like $70,000 of error. And wow, would you look at that? Just by using those additional sources of data, we dropped down to about $51,000 of error, which is, I mean, I think at this point, one of the best models available. So yeah, I will publish this, and everybody can jump to the top of the leaderboard if you want to. So we can use that. But of course, oh, we got an issue. Input X contains not a number. Oh, tragic. Okay. Ooh, okay. So this is actually this is a really, really good thing to run into. So what happened here? My guess is that there is either a city or a zip code that is not in our training set that shows up in our test set. And we could go and verify this, but I'm pretty sure that's what it is. And so when we come and we do our average up here, at the very beginning, when we say group by city and do a mean, and then group by zip code and do a mean, when we merge, if in our training set we have a value that isn't there, it'll freak out and it'll say, I don't know what you want from me, right? So one thing that we could imagine doing is just replacing it with the average. So what if we just said df, I believe this will end up with price. Oh, do we have to do this twice actually? Ugh. Does df merge actually have a way to handle numbers that aren't there? Let's check the documentation. No, it does not look like it has like a default value that you can put in. Okay, no bother. Well, one nice thing is we know we don't have any not a numbers in our training set, so we only have to do this for our test set. So we can say average state price. Oh, I guess it doesn't matter. So after we've added this column, average state price, we can just say fill NA, and we can just fill it with the average state price. So if there's not a state in there, which I mean states actually should be fine, but we can do it anyway. And then likewise, if the city is not in there and it's not a number, we can fill it with the average city price, which all these should end up just being the price, And you could imagine there are more elegant ways to impute these values. Like for example, if the zip code isn't there, you could still fill it with the average state price. Maybe that would be a little bit better. But let's see if that gets any better for us. Fingers crossed. Uh-oh. No, there are still... Oh, I think we need to actually... sorry, I'm sure I've been giving you whiplash just by scrolling up and down and up and down. When we do this, I think we actually need to reassign it to the column, because right now it's doing it and producing a series, but we're not actually doing anything with that series. So we're overwriting our column with the replacement column that has all the null values filled in. Cool. Where to publish the program code contribution in public, as mentioned earlier before, and the 4 options to win a prize. Yes. So when you have a notebook like this, you can click share, and all you got to do is just make it public. And if you have it attached to this competition, then it should just show up in the code spot. But this is not what I wanted. But if you just come over and click on code, you should see it show up here. And so I'll only look at things that show up here. If you're still having trouble publishing code that you wanna share, then I would get into discussions and open a question. Let's see. I don't know how it works in the States. Maybe there's also additional patterns in how zip codes are assigned. Yeah. I think Shenria answered this. Yeah, it kind of varies. In general, it's like high zip codes, low zip codes, it doesn't really matter. I mean, sure, your zip code might be indicative of your state. Like a lot of the zip codes in Seattle start with 9.8, right? I think all the zip codes in Seattle start with 9.8. So like, yeah, you could learn things that are around the 9.8 space, like our Seattle, but you already have the city name, so it's not really that helpful. Let's see. Oh, Dark Rules asks, so is there a way to know that from this point we are overfitting and we should stop there? Yeah, so this is a great question. And the thing that I would really draw your attention to is the difference between when you test it on data you have seen and when you test it on data you haven't seen. So I'm going to rerun this. Oh, wait, this is still zip code price. So when we come down here, when we do this run, this is all testing on data we haven't seen before, but we could also test it on data we have seen before, right? So if you wanted, you could rerun this whole block. And instead of, so here we're testing it on X test, but you could actually test it on X train, right? And then compare it against Y train. So here we're getting an average error of 50,000. And then when we test it on stuff we haven't seen before, we're getting an error of 51,000. And so those numbers are, yeah, it gets a little bit worse when we test our data, or we test our model on data it hasn't seen yet, but it doesn't get that much worse. And that's the thing that we really want to see, right? In general, you get this effect just by looking at, if you want to know, did a change I make improve it? Well, yeah, you should look at, test it on data you haven't seen before. And if that number is getting better, then usually you're generalizing well. But that's a great question. Let's see. Yeah, there definitely are. Okay, this actually this reminds me of a song by Lord. I love Lord, y'all. If there are any Lord fans on stream, I think Melodrama is one of the best albums ever written. But in her song, I think it was kind of her breakout single, Royals. She says the line, "No postcode envy." And I think this gets to the idea that yeah, there are certain, like, I don't know what the postcode for like Beverly Hills is. Let's see, Beverly Hills zip code. 902. Oh, 90210. That's like a zip code that I've heard of before, right? So yeah, if you were going to have postcode envy, then maybe 90210 would be a postcode you might have some envy of. Hey, we have some Lord fans. Love to see that. Yeah, I think there is like Beverly Hills. There was a show, Beverly Hills 90210. Yeah, but so yeah, this idea of some zip codes are like, you know, like known for having really bougie houses that are really expensive. Yeah, that's like totally an intuition we're building off of. Cool, cool. Jeffrey LGV, it is great to have you here. If you have any questions, please blurt them out. I appreciate that, you know, not everyone can join the stream right at the beginning. So yeah, if there are things that we kind of skimmed over that you're like, wait, what makes sense about that? Like, please ask and we'll go. Okay, sorry, I don't want to besmirch the good name of Pure Heroine. Also an incredible album. I will besmirch the name of Solar Power because I do think it is not her best work. But no, I think Pure Heroine is incredible off the charts. I think Melodrama is incredible off the charts. And I think Solar Power is just okay. It's not a bad album, but it's not, for me, it's not hitting the heights of Lord, you know? But hey, we have heard that she's coming out with a new album and that it's supposed to be like more like Melodrama. So there's going to be a little bit of a return to form. Right on. Yeah, apparently there's a Travis Scott song. So yeah, 90210. This is sort of classic. Yeah, classic postcode envy. Cool. So now let's get back. Now that we've added some more data, okay, we're able to predict correctly. Let's see. Age Action says, isn't there a train val curve that can indicate overtraining? Yes, there is, and that is something that we're going to do specific graphs of tomorrow. Yeah. This is, I think, in general, I mean, I think you totally can look at, like, I think usually you really like to see that validation and training curve when you're taking checkpoints at every iteration of training. Here, training happens so fast, we kind of don't care about it, but we will get into that tomorrow for sure. So now we can make a submission, and we should be able to submit this and blast to the top of the leaderboard. But yeah, what Age Action is talking about here is you can just look at a graph of how well does it perform on that data you have seen versus how well does it perform on data you haven't seen. And this can be a powerful tool to see like what's going on. Are we overfitting? Are we underfitting? Et cetera, et cetera. Let's see. Learning curve to identify overfitting, underfitting. Looks compelling. I will officially sanction that as pre-session reading. I like Towards Data Science. Towards Data Science is really good. All right, drum roll, please. Let's see how we did. Ooh, interesting. Spicy. Wait, let's see. Okay, so we did not do as good on this one. That's super interesting. So this maybe is a sign that there is something a little bit different about our training data and our test data, to the point where we were actually unable to do better on that data we truly hadn't seen before. So you might say, hey, Will, didn't we check to make sure we weren't overfitting? And the answer is yes, but we were only able to check on our training data set. And sometimes there are differences between your training and test data set that actually make it so that even though you're doing cross-validation, there's this idea of distributional shift. So for example, if our training set had a bunch of homes on the East Coast and our test set had a bunch of homes on the West Coast, we could still do better on data we hadn't seen before. But if it's all data that's the same, then we'll do better than something, truly different. Which that is, I'm a little bit surprised by that because I would have expected it to generalize a little bit better. Let's see. Did we dot all our I's and cross our T's? Yeah, it looks like we did. Another minor thing that you can do. This generally shouldn't have that big of an impact, but because we split out 20% of our data, we are training for our last model here on 80% of the data. And you sometimes can get a little bit of a boost on your actual submission if you just train on everything. So sometimes you can call this your final model. And we can fit our final model on just X and Y up here. So all of our training data we'll use in sort of the final boss battle. And this, of course, you cannot, you can't test this because you're using all of your data on it. But something worth trying, and maybe that'll get us a little bit better. But we will see. And I think we might leave it there. We can check back in with the leaderboard, and then tomorrow we'll be back here same time, and we will do some work in TensorFlow. So TensorFlow it is one of the sort of the big dogs when it comes to machine learning libraries. Scikitlearn, as I mentioned earlier, is really, really great because it's pretty simple to get up and started with. TensorFlow and Keras are more powerful and also can become a little bit more complex, which is, not all bad. But so TensorFlow and I would say TensorFlow, PyTorch, and Hugging Face are three libraries that are like, oh yeah, those are sort of the big deals. All right, let's see how we did. Wow, we did even a little bit worse. Okay, I probably shouldn't show this on stream, but this is the public score, and there is separately a quote unquote private score. I think if I go, actually, I would guess that it would show it here. I'm kind of curious to see if we do better on the private score. So the test data set is split into two, and you generally will only actually see the public data score, but the final standings will be determined by the private score. And so it is possible that you will do really, really good on the public, but if you, for whatever reason, didn't do well on the private, it would go down. Last date and time delay to make submission. Yeah, great question. So you can go over to overview, and I believe, okay, right here, timelines. You have 2 days to go. The end time is August 4th. So I think August 3rd is Friday. And so basically you have to do it by the end of the day on Friday. So two more days. So you'll have tomorrow, and then I guess Friday, everybody can kind of scramble for their last minute submissions. Let's see. Started working with Conda, ENVs, and VS Code a week or two ago. Kaggle seems so much better to work in. Thoughts? Yeah. So I won't lie. Like, I like Kaggle, especially when you are collaborating. Like in this kind of scenario where I'm doing some stuff and you're doing some stuff. It's really nice for that because we're all using the same version of things. There are certain things that I would say, oh, if you're doing that, then maybe you want to do it locally. It's definitely more hassle to do it locally, as I'm sure that you experienced like dealing with Conda and dealing with what version of the packages do I have can be a little bit annoying. But sometimes, for example, there will be a package that you can't get on Kaggle. Usually they have you can access the internet, so you should be able to download anything that you have locally. Sometimes you want to run on your own hardware, right? Kaggle does give you free GPUs, but like, hey, if you have a really powerful GPU in your lab or something, yeah, maybe you want to do that locally. Other things, yeah, maybe you have your own, like maybe you really love VS Code and you don't want to do this in Kaggle's editor. You really want to do it in VS Code. That's another reason. But yeah, in a lot of cases, I think the Kaggle is pretty nice for sure. Let's see. Polaroid is only seeing 140p. That's very bad. I hope the audio is better so you can hear how aghast I am at 140p. Shenmarie confirms that dealing with package versions is annoying. I feel that. School Crusher for Life. Can you explain what you did in revision 5? You added the test data into the training set, so it's both 80 plus 20. How was it worse then? Yeah, this is a good question. And on some level, I mean, so this is, let's go back to here. So what we were doing earlier was, in order to test our model, we were actually taking our training set and splitting it into a train and a test. So we kind of had a fake test set that we were able to test on. But that meant that even the last time that we fit our model, we were only actually training on 80% of the training data because we were holding 20% of it back, right? And the intuition was, yeah, like that's 20% of the data that we're not actually having any benefit from, so we could throw that in there and maybe do a little bit better. And I think the answer is that there is a little bit of randomness here. If you chose a different random state, it seems totally possible that you would maybe do better. In general, we wouldn't expect to usually see adding more data having our model generalize worse. I don't know, other things that I would throw out. So sometimes if you have multiple examples of something in your training set, so for example, what if in our training set we had lots of the same zip code? Then that might actually cause our model to sort of over-index on that one zip code. And if in our test set there aren't that many examples of that zip code, then maybe our model learns something that is not actually that helpful to us, right? I mean, here is actually another interesting thing that you could consider doing is, because our test set, we know all the zip codes, we know all the states, we know all the cities. You could actually think about removing data from our training set that doesn't reflect the test set that well. So, for example, if we don't have any cities from Cheyenne in our test set, you could think about removing the rows from our training set from Cheyenne, because whatever our model is going to learn about that, it might not actually be helpful. This is, I don't know. I don't want to push on this idea too much, because usually more data is better. But we might be kind of getting the limits to how predictive this data is here. I'm glad to hear I'm back in HD. So Skull Crusher, I hope that is helpful. To be totally honest, yeah, that's a little bit unintuitive to me as well. I mean, part of me thinks, would it be worth just double checking? I mean, I think it is worth double checking that things look right. We are training our linear regression model. X and Y just come from clean train, and we do up here, we do create a new clean train. Yeah. Yeah, I think I might just leave it at yeah, there's some randomness in here, and it is, oh, that's just with living area, isn't it? Yeah. But yeah, you could, I mean, one thing that would be kind of interesting that we could just do, we have a few minutes, is just to look at sort of distributions of things. Yeah, I mean, so this is a great point. Is more good data is better. Usually, more data is better, but more good data is always better. So something we could do is look at train and test. And we just look at state just for something easy. So we can get state, and we can do value counts. Because something that would be interesting to see is, oh, maybe in our test set, different states are more common. So we can see in our training set, Connecticut is the most common, followed by Indiana and Georgia. And maybe actually we just grab the first 5 here. And the first 5 most common, Indiana, Georgia, Connecticut, Delaware, and Colorado. So there certainly are some differences. I mean, these are all pretty tightly clustered, but like, yeah, Connecticut is relatively overrepresented in our training set compared to our test set, right? So you could imagine trying to rebalance that. You could repeat this game with zip code. Maybe actually city would be a better one to look at. So here again, a little bit of wobble. So Cheyenne, there are a lot of places in Cheyenne, and Cheyenne doesn't show up in the top 5 in our test set. So let's see, tangent. But is there a good reference for how to make a great Kaggle notebook like this, or is it not that important in the longer run? Ooh, I like. Let's see. It's really hard to copy things let's see. It really does not want me to copy stuff from the comment. But no, I would, if you sitting at home can copy that comment, I would totally take a look. Maybe I will just try to URL hack. Or maybe I'll just search in Kaggle and see how Kaggle searches. Let's see. Can I just go home and then search? Make your notebooks look better. This is by Moth, but this is maybe interesting. Oh, this is the same person. Tips and tricks. Oh, that's very fun. Yeah, I love this. Maybe I need to read this and try to make my notebooks prettier. Yeah, some of these are very, very neat. Interactive plots, very cool. I dig it. Yeah, I would say, I mean, definitely the most important thing about your notebook is the sort of underlying stuff. But when you get into, I would say think about what the notebook is for, and if you are going to be showing off the notebook, then yeah, I think totally it makes sense to put a little bit of love into it. I would say a little word of caution. It can be very easy to go overboard, right? I mean, it looks like most of the suggestions here just make it a little bit really just make it a little bit cleaner and cooler. But definitely there is a point where you can go a little bit too far. But yeah, I mean, this seems like a great guide. So yeah, we recommend that. Dark Rule is asked, is there any ML algo which assigns different weights to different parameters according to their influence on price? So a little bit of a cop-out, but this is, I mean, in some way, this is kind of what linear regression does, right? Like on some level, we had that number per square foot. And in some level, that's saying, well, this is how important square footage is to price, right? And if we looked at our bigger model that used all of our variables, all of them would have a different weight. And that weight is sort of how much that number will influence the price that we spit out. So I'd say on some level, that's kind of what linear regression is. Getting back to because it's linear, it can only think about things in linear terms. And there are, lots of different ways that things can influence price, right? So for example, maybe a townhome in the middle of Mississippi is not worth much, but a townhome in New York City is really, really cool. And so that sort of, there's a nonlinear relationship there where it's like an if this, then that, right? And this model really can't handle that, right? This model can't say this value means one thing in one context and a different thing in a different context. And that's actually what we're going to look at tomorrow. And we'll bring in artificial neural networks and we'll do deep learning. And we'll get a model that can handle a lot more sort of nuanced relationships between our different variables. And so that I'll tease you with this, and then I'll probably sign off. Is that another a phrase that people use to describe artificial neural networks all the time is automated feature engineering. So there's this idea that if you have a good enough neural network, it can actually figure out what features you need without you having to explicitly say, well, what about square feet squared? What about square feet cubed? Or whatever. So that is, I think, a fun thing to look forward to. Okay, cool. I will do the final sort of housekeeping thing here. So you are, oh, again, I guess I'll save this so everybody should be able to grab the public version. It didn't do quite as well as we thought it might, but it did do, it did get somewhere. We definitely improved. You can definitely get close to the top of the leaderboard now. But so here is our CAD competition. This is where you can publish your code. It looks like we already have 2 cool notebooks that I will take a look at when deciding who wins. You can always join the discussion. Oh, we've got a few more discussions, which we will take a look at that. I will take a look at that after I sign off. Our leaderboard is heating up. We have some really, really competitive submissions. We do, in fact, have an expert in there. Yeah, I would say meet me back here tomorrow for our last session, and happy hacking. I will play us out with Kalimba, and if there are any additional questions in the chat when I turn around, I will answer those, and we'll call it a day. All right, thanks, friends. I will see you tomorrow. Oh, thank you for all the sweet words. Bye.